Okay, everybody. Today I'm going to go over and explain and demonstrate how to analyze a mat foundation and pile group, and then go ahead and measure the settlement behavior. So first, I'm going to go and insert some points which will represent some borehole log information representing the different surface layers beneath the ground surface. So I'm going to go use this tabular input function and load from a file. I already have a text file here that contains XY coordinates, and they're going to be inputted into GTS, I can have an option here to make points as compound and then explode it later on, but I'll just directly input them as points in space. So if I zoom in here a little bit, I'm going to close the output window for now because I don't need it, and I'll use the front view to see the points in a different perspective. I'm going to go into the geometry and now create some point faces. So depending on how many points I have, it increases the resolution of the surface it's going to generate. So I'm just going to select the first layer here and preview, and you can see that the first layer is generated based on the points that I've inputted from the text file. Then I'll apply. Then I'll go ahead and select all the other points and preview this. And if there's any time there's going to be some points that don't match with your data, then you can always translate them in space or reposition them. But for today, I'll just leave them as they are. The next step here is to reposition the surfaces so that they are referenced appropriately. So what I'm going to do here is I'm going to move these two surfaces and translate them from its current position to somewhere at 0, 0, where I'm going to represent 0, 0 as the top ground surface. So I'll go ahead and select the whole entire object and then go right click, and then there's an option here called Transform Translate. But before I do that, I'm going to go first use this point option and try to select the midpoint of the surface. So I'll go here and there's an option here called Center of Points. And I'll pick these 4 points here, and then preview, and you can see this green dot appear, and that's going to be what the preprocessor determines to be the center point of the surface. So I'll apply. Then I'll go ahead and select the entire object, and then go to Transform Translate. I'll select that center point based on a 2-point vector. And because I know that I want to position it here at 0, 0, I can either click this point, or I can just type in 0, 0, 0 with no delimiters, and then update the distance and preview the translated object and apply. I'll zoom in and notice how the top surface is somewhere in the position 0, 0, 0. But I'm going to move this 10 meters below the ground surface. So I'll go ahead and select all the objects again, Transform Translate, and in this case I'll just use a simple the working coordinate system axis y, and then I'll just type in -10 to translate these objects down 10 meters below the ground surface. So here's my front view, and this is the 0, 0, 0 reference point. And now I'm going to zoom out and now start working with the working grid here. The working grid currently is in the global Z and X plane, and I want this to be flushed in the same plane as the X and Y. So I need to change the position by going to Geometry, Work Plane, and Move. And then I'm going to go ahead, and there's several different ways to move the work plane, but the easiest one, because I know the basic unit positions of the vector, I'm going to type in 1 for the x-axis and 1 in the y position, and then you'll notice that the plane has moved in the same plane as an x and y. So I'll click OK, and now I'm going to go to my top view, and you'll see where the top view, noticing that the planes are in the x and y. And you'll also notice that the grid here is quite coarse. So I'm going to increase the resolution of the grid to something more manageable. So in this case, 1 as the unit size, and I'll just generate 100 size grid, and then OK. So now you can see that the grid has increased its resolution, so it's easy for me to maybe model the mat in the latter steps. So the next step is to go ahead and model the core ground. And what I'll do here is first go into geometry, curve, and create on the work plane. I can select the rectangle wire here, and also I can select that same option in the quick shortcut key menu. And what I'm going to do here is try to encapsulate the whole entire soil, the whole entire soil surfaces that I generated in the previous steps. So I'll go to the top view, and using these grid lines, I'm going to go ahead and make sure my snap option is on for the grid, and try to just try to encapsulate and capture all the surface contours. Once I've generated the wireframe, I'm going to use this as my core ground position, an object, and I'm going to go ahead and extrude this wireframe by calling the extrude function, and then going into the filter and changing it to a wire. I'll use a simple extrude direction, the global Z and also the local Z position, and I'm going to go ahead and reverse this direction so it's going opposite, and then go down 80 meters and apply. And now you can see the core ground position being modeled and the two surfaces intersecting that solid. If you want to and the solid here it's quite it captures most of the characteristics of the ground, so I'm happy with this. So I'll go ahead and introduce those surfaces into the ground, and this is part of the modeling. So I'll use solid and divide, and basically I want to divide this solid with these two surfaces. So I'll select the solid and the two surfaces and apply. Now you know that now you can see visibly that the single solid object that was introduced is now divided into three parts. I'm going to change the view to top view, and what I'm going to do is introduce the rest of the ground by using the same extrude feature. So I'm going to go ahead and select the top, the faces in the Z and X plane with reference to the global coordinate system. I'll use the extrusion direction and have it moving in the global Y direction, and I'll move this to about 76 meters and apply. I'll do the same thing for the other side. I'll preview, and you can see the preview helps me identify which direction it is, so I'll reverse that. I'll do it for the other sides, and this is going to be with respect to the Z and Y plane. I'll select the extrusion direction, and I don't want to reverse the direction because it's going positive, and I'll do that to the same procedure in the next step. Alright, so basically we modeled the ground as accurately as possible based on our whole log data. And now we notice if we go into the geometry here, we have 27 solids representing 3 layers of soil. Since the 3 layers, there's only 3 layers, there's going to be only 3 material attributes going to be defined for each layer, and we don't necessarily need to have 27 solids. So what we're going to do is consolidate the solids into one solid. So I'll start with the bottom and just isolate this. Oops, let's show the solids again. And what I did here is, if you can see that the window here that I'm using is percolated. It's got it's dotted, right? And if you press Control, you'll see it's turned solid. And solids only capture the objects within the boundaries. But if I use the Control button and turn it into dotted lines, it'll capture only the solids that it touches. I'll go to the top view, and now because the third subsoil layer are going to share the same material attributes, I'm going to use this option called Boolean Fuse. This option will let me just basically designate one solid as the master, and then fuse the rest of the solids all into one solid. It takes some time to generate and delete all those solids and then generate the new single entity, but so you have to be a little bit patient. And then if we go ahead and view that, we can see that this object here is one single solid, and I'm going to designate a name called subsoil 3. I'll turn the rest of the solids on again, and I'll hide subsoil 3, and I'll just go ahead and hide the top layer. Go to the top view again, and this is going to be subsoil 2. So I'm going to use the same operation, Boolean fuse, select one object, and then select the rest, merge the faces together. And again, it takes some time to regenerate all the objects, all the solids again. But once it's done, we'll take a look, and you'll see this is one complete solid. And I'm going to go to the solid folder and rename this to subsoil 2. I'll turn on all the solids again and go to the side view, hide subsoil 3 and 2, and now go to the top view again and perform the same operation. Okay, so now if we go ahead and use the isometric view and turn on all the solids, I'm going to select the entire solid again, use the transparency to control how opaque it is, and then use the check duplicates to ensure that the geometry are showing duplicates between each of the solids. And this is going to be this is an important checking procedure prior to meshing. The next step is to model a mat, and what I'm going to do is toggle on the grid again. And because the dimensions of the mat is 10 by 10, I'm going to just enter the use this 2D rectangular option, and then type in the coordinates 5 and -5, and -10 by 10. And now you can see that the wireframe has been generated on the surface of the first sublayer. And what I'm going to do is I'm going to extrude this wireframe by first hiding all of these solids, hiding the grid, and I'm going to go to geometry, generator feature, and extrude. I'm going to change my filter to wire, select the wire that's representing the mat profile. I'll select the easy select direction axes in the global Z, and enter the length of 0.8. Or like 0.6 instead. Okay. Now I'll turn on the. I didn't give the subsoil layer 1 a naming convention, so I'll just type press F2 on the keyboard and type in subsoil 1, and I'll call this other object here mat. And if I turn these two objects on and go ahead and use the check duplicate function, you'll see that there's no relationship here. So I need to introduce the relationship between the subsoil 1 and the mat. So I'll use the Boolean cut feature to do this, and I'm going to use this subsoil 1 as the master, and I'm going to use the mat as the tool. I'm not going to delete any objects. I just want to just cut in a virtual surface between these two objects. Did I uncheck that? I better do that again. Boolean cut, master, and tool. I don't want to delete that. And now if I control transparency again, you notice all the solids have been regenerated, and we can see that the relationship between the mat and the subsoil 1 layer has been introduced. Okay, so the next step is to introduce the piles, and what I'm going to do is go into the top view. I'm going to hide all these soil layers, turn on my grid, and use this point option to create the piles, positions of the piles using these points. So basically, here's the pile group design for this example. And what I want to do is I'm going to first hide this mat and the wireframe, and I'm going to model the piles with a length of 27 meters and introduce a fixity which is going to be embedded into the mat with a length of 0.1 meter. So I've selected all 9 points, positions of the piles, and I'm going to go ahead and right click and translate these, or I can just translate one, it doesn't matter, but let's just do all of them. And I'll select the direction here, the global Z, use a non-uniform option, and this non-uniform option allows me to translate these points in bidirectionally. So in this case, I'm going to go up or down 27 meters and up by 1 meter, 0.1 meter. Maybe I need to do it the other way. 0.1 minus 27. Okay. So here you can see that the 0.1 has been introduced with reference to the original points that I've modeled in. And from the original reference point down 27 meters is the length of the pile. So I'm happy with this, and I'll go ahead and click OK. Notice that the original points are still here. I'm just going to get rid of them for now. I'm going to control the viewing position, toggle off my grid, and use this 3D point line and generate one line. I'm going to go ahead and select this line and then transform and translate this edge using a 2-point vector with uniform copies, which basically means I'm going to make multiple, and distance of 3, and update the multiple copies I want by 2, and apply. I'll select those three objects the two objects that I generated, including the original. I'll use a 2-point vector to determine the magnitude and direction, update the distance, and preview, and I've just generated now all 9 of my piles at the geometry level. I'll turn on the mat, and if we go to the side view, you'll notice that the 0.1 meter that I introduced is embedded in the mat. If you want to do some color coordination, you can go ahead and use this option here called Shape Color. Select all the objects here, uncheck all of the shape types that you want to not consider, but turn back the solid on and apply. And you can see that the preprocessor will automatically assign random colors to each of the solids. The next step is to go ahead and begin meshing. So what I'm going to do is not introduce any of the material parameters. That's going to be, you can go ahead and do that later on. But what I'm going to do is just import some previous attributes that I've defined with topsoil, mid-soil, bottom soil. We have a raft, wall if you want to introduce some excavations, and diaphragm wall, and some pile attributes that contain piles of the cross-sectional properties and the flexural rigidity of the pile, the soil structural interface parameters, and the raft and pile interface. And I'm going to go ahead and just select what I want. Give everything a new numbering scheme. And you can see that the sequence is a little bit off. It goes 1, 2, 3, there's no 5, but because I've assigned new IDs to each of these when they get imported, if I click OK, we can see that sequence has been rearranged to 1, 2, 3, 4, 5, 6, 7. So what I'm going to do now is, because of the high stress gradients around the area of the pile and the mat, I'm going to go ahead and just show only the mat, and I'm going to mesh this using the auto mesher solid with an element size of 0.5. I'm going to go ahead and turn on subsoil layer 1 and auto mesh this using a recommended value of 20. Assign the attribute topsoil, give it a name, topsoil, and apply. And you can see that as we move away from the area where there's high stress gradients, the mesh becomes more coarse. So this is the general idea in meshing, that the areas where there are going to be great changes in stress gradients and changes in the displacements, the area of concentration, basically, based on the same Venant's principle, we can just have this area very, very fine with an acceptable element size of well, there's meshing practices that you can do, such as like a parametric study on meshing, but at this fine level, it's a good start. And then as we move away, the stress gradients are not really going to be that important anymore. So I'll turn on subsoil 2 and perform the same procedure as I did before using the AutoMesh Solid. The preprocessor has recommended me 6, but I'll just stick with the 20 and go to my midsoil attribute. Type in midsoil as the name, and you can see that the subsoil 2 has been meshed, and I'll turn on 3 and perform the same operation, but this one's a little bit thicker, so I'll give it an element size of 25. Assign the attribute bottom soil and type in bottom soil and mesh. Now at this stage we need to go ahead and check for free faces. Free faces indicates that there's nodal incompatibility. And you can see that there's no free faces lying within the boundaries of the mesh set, and that is showing that we did a good modeling job. And that's partly due to the first check we did at the geometry level with the check duplicates. If you see areas where there's yellow surfaces between two solid objects, this is one checking feature that you can do prior to meshing that will ensure that there's proper nodal connectivity between each mesh set that's generated. So I'm going to go turn off all the mesh sets, and I'm going to turn on my curves. And what I'm going to do here is first I'm going to show you how to model the pile elements. The first step is to turn on your edges that are going to be representing your piles. I'm going to select all 9 piles here and give it a division of 1, and give it a name, say piles, and apply. So if you go to the mesh folder and look at the piles, and then you can view the nodes, you can see that there's 2 nodes that have no relationship whatsoever to the mat or the ground. These will need to be constrained later on, as I'll show when we apply the pile boundary conditions. The next step is to go into the model and element, and you can go into the create pile option and select the type of 3D pile element that you want to generate. So I'll go ahead and select the pile to sort interface first and apply. And then now you can see that an interface element has been introduced between the original pile and the soil, and that's because you can clearly see that based on the new types of nodes that have been generated. These nodes are going to be connecting to the solid element and making that relationship. What I'm going to do next is go ahead and turn on my mat, and you'll see if I go and hide all my data and get rid of this wireframe, you'll see that the piles again are still embedded here, and I'm going to hide the original pile element. And what I want to do is I want to change the interface properties. If you go to model, display, and go to attribute, you can see I have a RAV interface attribute number 7. Right now they're currently assigned 6. The interface element that's supposed to capture the structure interaction is represented as 6. What we can do is go into model, element, and change parameter function and select the 1D attribute, because these are all 1D elements. And I'm going to use this filter to only select the 1D elements that are embedded in the mat. And I'm going to make sure that the attribute pile to RAV interface has been selected, and I'm going to go ahead and select these 3 and the next 3, so I have 6, and I should have about 9 in total. And then go ahead and click OK. And now if I go and apply, let's go ahead and show the IDs. You can see that 7 attribute number 7 has been applied to the tips that are embedded in the embedded in the mat. Okay. The next step is to go ahead and turn on the piles, and then just apply that boundary condition that I mentioned before. we don't necessarily need to apply the whole entire boundary conditions to the whole pile, but let's call this pile boundary condition pile and rotational constraints. These rotational constraints are used just because that we introduced these beam elements here and here, but they have no constraints whatsoever. So we'll just apply this condition here and click OK. The next step is to go and turn on all the mesh sets and give the entire model ground supports. And I'll use a generic name called BC and apply. And finally, I'll go to my model and load and give this model a direction of gravity in the global Z, -1. Okay. Oops, something's happening to my video. I have no idea what's happening. Alright. So here, if we go to the analysis tab, you'll see that the boundary conditions that we assigned are already here. Same with the self-weight. I can turn them on and off, whatever. We'll go into the isoparametric view and take a look at our entire model. And maybe we want to apply a load here. So let's go to model, load, and the pressure load, and I'll just type in the load set 100 or 100 kilonewtons in the normal direction. I'll type in 100 here. Face pressure on the element face. Preview and apply. And now I'm going to go ahead and define my construct stage. So in the first stage, I'll call this in situ. And what I'm going to do is drag and drop the elements that I want to consider. So the mid-soil is this mid-soil, topsoil, and the bottom. The ground supports and the self-weight. I'm going to clear the displacements in the first stage and save. In the new stage, I'm going to call this installation. And now install my mat, my pile, and my interface, and my interface element. The interface here. This is a tip has been generated, so I'll just leave that out. And my boundary conditions for the pile, and save. And finally, I'm going to apply a pressure load, a vertical load, and I'm going to introduce some load steps, say about 5 for now, to achieve better convergence. And I'll call this vertical load, and save. So now the model is ready, and I'm going to go ahead and look at this tip. So tips were introduced in the model, so I guess I'll just go back to the construction stage and let's go ahead and activate that tip there. I'll turn on all the mesh sets again, and I'm going to use this show elements activated, and now I can go through each stage. So in the first stage, I have just the ground and perform the initial static analysis. Now in the second stage, I install the piles and the mat. And then in the third stage, I have a load introducing steps of 5. Once I've defined the construction stage, I'm going to go ahead and create an analysis case. Close test and select the construction stage. Go to the analysis control. Turn on my initial stage for stress analysis to start at the in situ stage, and also my K-naught condition. And close. Now I'm ready to solve, and before I do that, I'm going to change my results from center to node, and go ahead and solve. If I haven't saved, I gotta save this in a new folder, so I'll go and create a new folder in my G drive called test. It's already one created, so I'll just generate one here, test. Here you can see that a dialog box appears showing you the convergence behavior, and I'm going to turn on the output window as well. So here you can see that the 0 iterations represents a horizontal line in the graph representing that convergence was quite accurate, quite fast, required no iterations. We're in phase 3, and now we've introduced the load steps, and it's already solved for the first already 5 steps quite fast. Alright, so now apparently the whole analysis has completed in quite a short time. I'll go into the post processor, and now you can see each of my construction stages, including the load steps with their corresponding names. I'll go into the first stage and just check out my vertical my displacements, and yes, they are cleared. And if I go through each stage, I can see that the displacements change with respect to the load applications. If I just want to just see only the settlement behavior, not of the ground, I can just go ahead and hide my mat. You can see what's happening, and then I can go ahead and use the deform shape, say in the Z position, and take a view and check out the deformed shape of the model. Use the post command, and also to see what's happening inside the model at the same time. Now let's go ahead and take a look at the piles, and we can go ahead and turn them on. And I'm going to go back to my post command and view and turn it back into original to show all of the piles. And we have introduced vertical stresses, so we can go ahead and review the results of the 1D element forces in the local x direction. And as we move through each stage, we can see that the axial stress increases with respect to each load step. And here's the bending behavior, initial bending behavior, which is all pretty much garbage. And when we go through the next stage, we can see the bending behavior depending on the differential settlement. If you want to see the shear forces at what the pile is for the embedded pile, just go ahead and go into the pile element, and you can see the shear force along the x. And we probably need to turn on the interface element here, and you can see that the shear forces here are quite high due to the vertical loads being applied. If you want to see the shear force of the pile itself and not the interface, you go ahead and turn off the interface element, go to the post processor, and select FZ. And this is the shear force of the pile. If I go ahead and turn on the entire model, and we can go ahead and review the 3D element stresses in the vertical direction. And for each layer, we can go ahead and see what the vertical horizontal stresses are by simply using this maybe command here. Let's go and just show, let's do that again. I'll just show only the top layer here. Post processor and my vertical stress. And no deform shape. So the center vertical stress is showing a plot diagram as like this, and the horizontal and the other horizontal in the other direction, x and y respectively. So here's the initial, and as we move through, if I show the total, you can go ahead and use the probe result and also extract the results in this manner. Be sure to use the center value. And if you're looking at a specific value for demonstration purpose, for presentation purposes, you can use this isosurface, and going to the window, the property, if you want, you can if you have a desired value that you want to see, you can go ahead and apply, and also show preview them all at the same time. Okay, so thank you very much, and have a nice day.